We're going to shift gears here and look at matched pair analysis, which I also call dependent variable analysis. And it really does fit in the analysis of variance chapter. So I'll explain. But the problem I'm looking at is on page 519. It's problem number 38. And here's how it reads. Table 11.20, which I've copied on the board here, shows data on times and minutes of relief of headaches for a standard and a new treatment. We want to see if there is a difference between the two treatments. So here we have 10 people, persons 1 through 10, and they walk in with headaches and they're given the standard treatment. Whether it be aspirin, Tylenol, I don't know what it is. But anyway, these are the minutes before they probably hit a button and say, oh, I'm starting to feel relief from my headache. So first person got headache relief in 8.4 minutes, next one 7.7, so on down the list. The average for this group was 8.43 minutes. So then they brought them in a different time, still have a headache, and gave them something new. Maybe they're testing a new drug, a new treatment. And so look at what happened to person 1. It took only 6.9 minutes this time to get headache relief instead of 8.4. So he improved. Person 2 improved. 7.7 down to 6.8. Person 3, I think, is the only one on this list who actually went backwards. It took just a little longer for that new treatment to kick in. But everybody else was dropping here, I think, if you look carefully. And so the average for the new treatment is 7.68. So there are actually two ways to study this, to analyze it. And the first way is what we did in chapter 7, which was comparing the means of two samples. And so if I look at the first mean, x bar was 1 was 8.43 and x bar 2 was 7.68. If we compared those means using calculations, I think it's on page 250, let's look that up. Oh, that's confidence intervals, I'm sorry. Page 295, testing the difference between two means. This should look familiar to you. We did this in chapter 7. And this was the calculation that was one of the worst that we had to do. We had to calculate an S, a pooled estimate for the standard deviation, and then calculate the t-score. And, well, the author's done that for us. Because he says in the book, he says, an ordinary t-test for the difference between two means results in a non-significant t equal 1.15 with 18 degrees of freedom, p equals to 0.13. So p-value was large for the difference between two means. And so is there a significant difference between the two means? No. In other words, there's not enough evidence here to show that the new treatment is any better than the old treatment. Although you might argue, well, wait a minute, 9 out of 10 people improved. Well, statistically, using laws of probability and all the theorems, it's still not enough. And so we can't conclude that on average, everybody getting the standard treatment will do worse than everybody getting the new treatment. We can't say that with at least 95% confidence. Actually, our confidence would be 87%, wouldn't it? All right, so that's comparing the difference of two means. Now, in this case, we're treating the variables as if they're independent, as if one has nothing to do with the other. And so I take this column of numbers, find its mean, standard deviation. Take this column of numbers, find its mean and standard deviation. I'm treating them as if one has nothing to do with the other. In other words, they're independent. And so that's independent variable analysis, testing two means. Well, we have something new in this problem that we haven't faced before with this type of data. That the two columns are dependent upon the person. And so these two numbers are dependent upon person 1. These two numbers are dependent upon person 2. And so before, when I looked at it this way as independent variable analysis, if suppose I just took these numbers up here and switched them around at random, paired up numbers differently person to person, I would still get the same means, I would still get the same p-value because we're treating them as if they're independent. But here, if we look at this differently, we say, well wait a minute, these two numbers are dependent upon the person. You know, this person here jumped from 9.0 to 6.1. And so another way of looking at this is looking at it as if this data is dependent. In other words, if one variable depends upon another, or depends upon the specific sample. And so we're matching these numbers together with the person by person, item by item. That's matched pair analysis. And so that's and now if you did juggle these numbers around, you would get a different type of analysis, wouldn't you? Because if I juggle around looking person to person, now it's really changing the data. So I think that'll be a little clearer as I do a little more writing up here. By the way, what does this have to do with analysis of variance? Well, the analysis of variance is the independent variable analysis. It is the comparing the difference between two means, because we have two categories. Two categories. Those are the means of the two categories. And so the independent variable is the type of treatment, and there are two categories: standard treatment and new treatment. And then the metric variable is the number of minutes. And so this would show up as a bar graph, literally something like this. Two categories, standard and new, and here are the minutes. And the averages are 8.43, and this average was 7.68. Is one bar significantly higher than the other? Well, that is testing two means. But so that's where analysis of variance comes into play, why that shows up in this chapter. But and you could do sum of squares instead of testing the difference between two means. Well, now let's look at the matched pair analysis. So kind of forget this approach, and let's look at the individual differences between standard and new. So I'm going to create another column here, and this is the difference. And in this case, because these numbers are larger than those numbers, in most cases I'm going to subtract it. I'm going to take standard minus new. So I create a whole new column of numbers here. 8.4 minus 6.9 is 1.5. 7.7 minus 6.8 is 0.9. This one's negative 0.2. Then 0.2, 1.3, 0.3, 2.9, 0.3, 0.1, 0.2. Okay. Yep, there we go. So those are the differences, and I want to find its average. And I have calculated that. The average, which I'm going to call D bar, is 0.75. So the mean difference, person to person, is 0.75. And so let's see here. I gotta find my data here. Oops. Wrong calculator. Let me try this one. I did this the other night in class, and so I think I still have the data up here. There it is. Okay. So yeah, the mean difference was 0.75. So D bar 0.75. The standard deviation of the differences is 0.93. So I had to calculate standard deviation. I don't expect you to do these calculations here. A problem like this, I will give you the calculation, and then you work with it from there. So again, it's not a number crunching class, so I'll give that to you. And sample size was 10. So here's the question. Looking at it this way, is it possible that this number is significantly different from 0? In other words, if there was no difference, if the difference was 0 between the groups, delta equals to 0. That's, I hate to do this to you, but consistent with what these statisticians do, they use Greek letters for population numbers, and so the Greek letter for D is delta, and delta looks like this funny thing here. This means there's no difference. Person to person, there's no difference. And the alternative hypothesis, in this case, since this is positive, delta would be greater than 0. That means that standard minus new treatment would be positive. So that's what we want to look at. Not the difference between the means of the groups, but we look at individual differences. We want to know, taking into account all those individual differences, is this really different than 0? Is it significantly different from 0? 0.75 is kind of close to 0, so the jury is out on this. But we need to do a t-test, and I've got to erase part of the data here to make room. So this is testing a single mean, and happily it's a shorter calculation than testing two means. And so we still have to go back to chapter 7. It's a chapter 7 calculation. Let's see, page 294 maybe? Yes, page 294, testing a single mean. The t-score that we calculate, it would normally be, you might write it this way as d bar minus delta over s d bar divided by the square root of n. But if we're testing to see if this is 0 or not, then this number is 0. So why don't we simplify this calculation? I'll make it d bar times the square root of n over s. So I put a 0 there and inverted and multiplied this fraction. So I have d bar times square root of n over the standard deviation s d bar. And we plug those numbers in. The t-score is 0.75 times the square root of 10 divided by 0.93. And I think it's, going from memory, I think it's 2.55. Let's go ahead and double check here. 0.75 times the square root of 10 divided by 0.93 is 2.55. There we go. So let's look that up. That's our magic number here. And notice that's different from what the book got when they looked at this as independent samples rather than dependent samples. When they compare the two means without taking into regard person by person. Their t-score was 1.15. We got 2.55 for this type of analysis. And so we need to, oh, there goes my calculator. We need to run off to page 650 maybe. 650, we have 9 degrees of freedom, and 2.55 is between 0.25 and 0.0100, between 1% and 2.5%. So the p value, let's say, is less than 0.025. It's clearly under 5%. That's kind of gist of it. And so now we have a really different conclusion. According to matched pair analysis, the new treatment does improve, is an improvement, significant improvement. And so it is a better treatment. So why might this be? When we, it seems like we lose some personal information when we just compare the means of the samples. But when we go person by person, is there improvement? I think that's getting closer to the real data there. And this is a great example because the author rigged the numbers so that you would see this difference between the independent analysis and the dependent analysis, or comparing two means versus matched pair analysis, looking at whether the differences are different from 0 or not. So to me, it's a great problem to illustrate this idea. And to kind of expand on that, when would you use matched pair analysis? I kind of like to think of it as a before and after scenario. Before we gave them the standard treatment, after we gave them the new treatment. What if I had, here's an example. What if I had 2 different classes, and I wanted to look at the final exams in both classes? All right. So I would take the average of the first class, I would take the average of the second class, compare the means. That would be independent analysis. I'd be comparing the difference between 2 means. And because one class is independent of the other. But here's a different problem, kind of similar. And by the way, in that independent analysis, what really gives it off is that the sample sizes are different. You can't have matched pair analysis. But think about this different example. Suppose I had a class I wanted to look at. I wanted to see if people improved from the midterm to the final exam. Was there an improvement from midterm to final? So my first column is the midterm grades. Second column is the final grades. And there I can just take the averages of midterm to final and see if the class as a whole improved or not, or got worse. And so that would be doing an independent analysis just on the means alone. But if I took person by person to see if did each person improve on average or get worse, whatever the case may be. And so we could, in this case, there is sort of a before and after. Before they took the midterm, after they took the final exam. And so each pair of data is linked to a single person. And so that's matched pair analysis. So we could take those differences, whether they improved or not, write those differences down, and then check to see if the average of those differences is different from 0. That's matched pair analysis. So you might think of like before and after type of stuff. Problem 42 on page 521. If you look at that briefly here, this, depending on what class you are, you may have this as a homework assignment. It says this is a famous data set collected by Charles Darwin. The data shows in inches the heights of plants grown in 15 pairs. One member of each pair was cross-fertilized and the other was self-fertilized. Darwin was interested in whether there was any difference in heights between the 2 groups. So Darwin was doing some primitive statistics here back in the 1800s, and he was quite a scientist. And so this is begging for matched pair analysis also. And so what it is, he's got 2 plants paired together in a mound. Like, okay, right here we're going to plant these 2 plants. Then we'll separate a while, we'll plant 2 more plants. And as the growing season progresses, one of them we're going to cross-fertilize with other plants, and one of them we're just going to hand-fertilize ourselves with the pollen, however that works. And so it's a little questionable whether you would use matched pair analysis there, because they're asking you to treat each pair of plants as if it's somehow the same plant. Now, in essence, they have the same soil growing conditions, sunlight, and everything else. And but they're saying, well, let's use matched pair analysis. Let's assume it's basically the same plant, fertilized 2 different ways. So I think it's probably legitimate enough scientifically, but that's a matched pair analysis. So anyway, that's how we'll end this chapter, with matched pair analysis, and it's a different way of looking at the data. And the matched pair analysis itself, strictly speaking, does not look like analysis of variance to me. We're comparing the means of 2 samples. That's matched pair analysis. That's analysis of variance. So, but anyway, it's a different type of data that we're considering here.